before I continue here, I'm going to ask you, how many of you have actually or are actually using apps on smartphones to see if they are working sufficiently every day? You're not? Come on, don't be shy.
I didn't get the question correctly. I didn't get the question correctly.
How many of you are using smartphone apps to count your steps?
Yeah. Oh, yeah.
Podometer. Ah, quite a lot. Do you think it's working fine? So what do you think? Is it accurate? No. Why?
Because our stride lengths are different for each individual.
But stride length is already a measurement. I'm just counting steps. So even if I don't have length, it's okay. So globally, what you find out is that it's very optimistic. And there is a reason behind it. Maybe in the conclusion, I will tell you why. So this is the structure of the presentation. It's very classic, so I won't go through it. Why it is important to have accurate step detections? First, I will say, how many of you in this room, we are not that many this morning. I guess people are still sleeping. Anyway, but even with that number, I have more people using an app to count steps than people not using it already in this room, okay? But in fact, the main application here is, I would say, health. We have navigation behind it, fitness and so on, but we are more and more getting toward more important application, I would say, for vulnerable users or emergency situation. Some of them are, for example, false detection. I've been conducting research with past students where if you basically assess the duration of consecutive steps, so basically when I walk, I have a step and another one, and I actually get like the correct duration, which start to relate to the stride length. You can use some statistical models from biometry approaches, and you can anticipate falls. But this anticipation only relates to the quality of the step duration measurement. And the step duration measurements quality only relates to detecting correct steps. So if you basically detect steps when you are cooking, then it means nothing. Okay. So the thing is that what happens is that it's became popular, you guys are using it, and in fact, it's now more and more used for critical application. So the question comes like, is it doable to actually get more robust step detection there? If you go there, then the question starts with like, what is a robust step detection and what is not? So as I said, if I'm actually cooking and I get steps detected, then definitively it's not robust. But it could be also that I'm actually using a smartphone and suddenly while I'm walking, I pick up a phone call and then I go back and then I get an additional steps. If you want to try, when I make fun, I usually to say to people, just go to the toilet, sit and go like this. You will see you are still walking. Okay. So the problem is like, what do we define as mimic walking signals, walking and so on, as compared to like real signals? And when you start this question, I've been working on pedestrian navigation for more than 20 years now. It's become a little bit of an infinite problem. Because is it doable really to define all those like mimic motion? Potentially not. So the question is like, indeed, I won't be able to define all abnormal movements that will lead to false detection. But what I know is what is normal. So the principal idea is that instead of concentrated on understanding everything that is abnormal, can we just focus on what is normal walking with reliable devices and learn from that? And this is what we've been doing with like a semi-supervised learning approach. So basically, here what we say is that we're going to learn on everything that is normal, and whatever is not normal is going to deviate from the normal pattern. So we don't need to learn anything that is abnormal. We will just distinguish the anomaly based on the normal walking pattern. So how do we realize that? We are going to work, of course, with signals. So we apply that to initial signals that are collected with wearable sensors. So wearable sensors, of course, at first it's your smartphone, but it can be a smartwatch. Maybe tomorrow it will be smart glasses. After tomorrow, it will be smart insoles in the shoes, etc., up to potentially smart textile tomorrow. And we take the signals, and at first we divide it into samples. And the samples here, the length of the duration is like 2 seconds. Globally, physically, because many times we forget about the physics, the classic step frequency of someone is 2 times per second. So you do 2 steps per second, more or less, in average. So it's 2 hertz. So in fact, if we want to capture a signal, we need to cover the duration of like a stride, meaning 2 steps. So we go for 2 seconds. And we go here with a 90% overlap. And then we're going to search into the features that are very interesting for understanding normal walking. And those features are actually extracted in the spectrogram. So basically, we transform the signals as it is, which is a time series of data, into time frequency features. And then we normalize. Normalize is very important. And here, to have the highest understanding or the best understanding of normal walking, we do 2 kinds of normalization. Maximum and minimum power values are used to normalize globally the signals and locally. You can look into the paper for more details if you want. Because here it also illustrated normalizing the accelerometers individually will actually improve the differences between the different approaches and the different case you have in the power distribution. So if you look at walking, it's, I mean, as it is, it's like a steady kind of approach. So if you really want to highlight what happens in terms of changes, you try to emphasize, like you would be reading a book and it's in the dark, so you take a light and you highlight the differences. So here to highlight it, we actually normalize because we have scattered power across the different frequency. And then we pull max, min, and min pulling operation. So we extract more sharp features and we reduce dimensionality. So we retain only the key pattern. And when we've done that, we use an autoencoder structure. So the encoder is going to compress the spectrogram input into a low-dimensional latent representation. Once we've done that, we reconstruct the 6 spectrogram from the latent space. So basically here, the idea is that we are going to learn from normal signals. So we are reducing the dimensionality of the learned signals or the normal pattern through the autoencoder. And then when this is done, we can actually improve this learning by training on normal signals. And whenever we will receive a signals, we're going to use the autoencoder to reconstruct the normal pattern. If the reconstruction error is high, then we deduct that we are not measuring normal pattern. And this is what is interesting here, is really to think the opposite. So you learn normal so that you can learn abnormal. Okay. So here you have an illustration of this reconstruct error. So you have here 2 data. In blue, you have the normal data here, which corresponds to expected Gaussian distribution, which is here centered and pretty low. And then you have here the abnormal data that has been collected with many different data sets. And the main problems comes from this region here. Because here the reconstruction error between the 2 is overlapping. So you still need to address this. Myself, I've been doing research for blind persons for many years now. This is one of my main outcomes these days. And in fact, this pattern here will change depending on who you are. So typically, if you're a sighted person, you're going to look into your environment and you're going to anticipate obstacles. So you will have a more steady pattern, and whenever abnormal is coming, it's okay. You will not have such a big overlap. Now, if you're a blind person, what's going to happen is that many times you search obstacles, like when you want to, like, for example, cross a street, or when you eat. If you see videos, it happens that blind person, they walk like this, and then they're going to eat, and then they're going to search. So in fact, depending on who you are and the target people, you may have to work a little bit on how to get the best threshold between the different populations. So that's a little bit, I would say, the limit of it. So here, just to do a first testing, we are actually going to publish more results in the next conferences on how it propagates into fall detection errors and also positioning errors. But here, for the first data set, we collected several data sets where we created scenarios. So what you see here is a typical scenario. Someone is actually walking and is getting a phone call, typically. Or you can have other stuff where here, for example, someone is actually on a chair and is texting SMS, short messages, etc. So this typically will count steps. We did acquisition with 8 participants, 40 kilometers in total, 3 different phone modes. So like the texting is like the SMS or navigation. The pocket is you have it in the pocket or here. And the swinging case, it would be like the smartwatch, basically you swing. And we also tested the approach on public data sets, open science, that contain actually 24 participants with the phone in pocket. So what we see here is that you have the confusion matrix and you have the distribution of the performance metric. So you can see that it's working very well. The true positive rate is 95%, with a true negative rate of 82%. And globally, I don't need to run out for emergency situation. So we see that the concept as it is actually very efficient, since we have like a very good results in terms of identifying what is normal from abnormal here. And if we look in terms of computational complexity, because we want our stuff to be running on in real time, we actually compared our approach with like another system that is called MobileNet V2. MobileNet V2 was chosen because it's a lightweight deep learning model that was designed for a mobile and embedded device. And it's commonly used in applications like image classification, object selections, etc., etc., where actually computational efficiency is critical. So, and you can see that if we compare our computational effort with this method, we are very fast. The reason we look at that in my lab is because we go up to the demonstrator. So we actually develop apps. We do the real-time coding on Android devices. We are going to publish in PLANS conference that will be in the US in April. The code, the entire code for that will be published in open in Python. And we are also going to publish the data set, more extensive than that one. And we are actually now pushing on a Google Store an app where you will be able to use it to get like correct step detection and the raw data from the Android devices. So everything will be published, and it's about to get ready very soon. So what are the lessons for that? The lessons is that to get something robust in terms of anomaly detections, because we consider abnormal as anomaly, we here proposed a semi-supervised algorithm to distinguish both and reduce false step detection. So basically, we learn normal to discover abnormal. And this is, for me in my lab, it's providing, for the first time, very good results, because we've been trying to learn mimic and abnormal motions for many, many times. And where it's also very interesting is that it actually demonstrates robust performances across different scenarios, including the public data set. So here we also tested it on a public data set, which was not actually designed and used for the training here. And it actually shows it's very simple, like detecting steps. It's not like a complex story when I talk about it like this, but it has a lot of practical implementation, as we discussed before. So here, for the future work, we actually, we have already integrated it with what we call in our lab smart steps, which is like detecting accurate steps and also step instant. So it's not only like knowing I have a steps, but it's being able to extract the step duration. So we go up to the microsecond in terms of detecting it. And then we use it for integration with pedestrian dead reckoning systems. So I don't know if some of you are familiar with it, but it's systems where you actually compute your position in space using only inertial signals. So you don't use any infrastructure. And it's called dead reckoning because you propagate the position. And you propagate the position based on step detected. And as I said, everything is going to be published in open source very soon. So you can follow what we are actually doing. So coming back to my initial questions, what do you think? Do you get more steps on your app than what you're actually doing, or do you get less with more? And why? Exactly. And why is it something that I would say most of like the GAFA, Google, Apple, etc., actually appreciating? The fact that there are more steps. I mean, it could be disturbing. They could be trying to fight for it, but in fact not. Nothing really is done.
The purpose for smart purchase is to give them a gross estimate of how many steps you go. So it serves the purpose to some extent, so that's why it cannot worry.
Yeah, so basically, if you go one step further, it actually serves the purpose of giving a good and positive image of the site. So that's the reason why it's not disturbing anyway. Thank you.
Thank you.